But if you are missing nearly all of them, that they see that something's going wrong. That something's going wrong.
Right.
So this is, and especially when someone from a foreign country, from abroad, is coming, then it's more obligatory. It means the director is insisting on people to come for the presentation.
Yeah, right. Well, I mean, it's hard to push people to...
Yeah, it's always hard, but we have methods for this. It means if we don't do this, then on presentation there will be a lot of empty places.
Yes.
So it's just, yeah, it is also, it means it's not only one presentation, one. Try this if it works now. Yes. It should. Okay.
Yeah.
It should work.
Yeah.
Okay. So this is how things are doing in Poland. I don't know if it's not obligatory. As I said, you don't have to go to all of them, but just select at least half of them, which you think are most important for you or can be of some interest for you, and then you go for them. But not to just leave or miss all of them.
Right, yeah. I don't think that people will receive.
Well, it's yeah. Now, if it's not obligatory here, it will be hard to introduce this.
Right.
In our university, it was always like this. So we didn't have any option. We just have to attend this, and we agree for this because it is like it used to be for a long time before. And now, if you are accustomed to just going from time to time, it will be hard to change these customs.
Right. So one of the things that it could be done is that, for example, the students, which are the future researchers, you can try to put some rules about.
Okay. That you know, don't push it to students. It means in Poland, these presentations are not for students.
Right.
They are only for researchers.
Oh, really?
Yes. Students, well, they can come, but there is not enough space for them. It means we have some free, several, but sometimes at presentation, people are just sitting somewhere at corners because there is no place. So students can,
like this, right?
Actually, we have kind of auditorium, maybe with less number of places here, but it's full. It means as everyone needs, as everyone has to come and hear to the presentation, there's no place, and we are a lot of students. I mean, PhD students, not the students for masters or students for PhD students. Yeah, they have to come, but not the other students. It means below masters.
Okay.
So that's why I said I told you that don't push it to students. You are researchers. This is research. So actually, if you are presenting something like this, hear to other people.
I mean, the point is that if you start to push in the PhD and master students, if they are more or less or generally attending to the colloquiums, they will at some point take it as a normal thing, no? Going to colloquiums and all that.
So as a start point, so as a starting, if you have enough place, it's something different than in Poland. We just don't have enough place because there are a lot of researchers there. In the institute, there are like, 60 or 70. I don't know how many places here we have, but it's like 6 rows. So this is just what we have in our auditorium. It is a smaller one. We have larger, but the presentations are given usually in a smaller one. So and this is for research, and we have the same number of PhD students. So they are sitting everywhere at the corners. And I cannot imagine to invite also students from below masters, so not PhD students. So this is.
Yeah. Okay.
Okay.
So let's wait a minute. Are you a faculty member in the university?
At my university in Poland, yes, I am. But it's not astronomy.
Yeah.
It means it's actually automatic control.
Yeah.
Bueno, creo que podemos technology Poland. He's a faculty member there, and today he will talk us about the PSF photometry for BRITE nano-satellite missions. So,
okay,
thanks.
Thank you very much for introduction. Yes, I'm from Poland, and I'm again in Mexico. In Mexico City, it's it's my pleasure to be here again after 2 years, collaborating also with my colleague Valery Orlov. Today, actually, I have 2 presentations, but I don't know how much time I will spend describing the things with nanosatellites. So if there was enough time, I will just switch the presentation. Okay, so again, as 2 years ago, when I was talking about BRITE nanosatellite, this time I will also show you a new method for photometry, which we do with our constellation of nanosatellites. It's called BRITE. So the BRITE constellation, BRITE mission stands for Brightest Target Explorer. It means we observe the brightest stars in the sky, usually the ones which are also visible, noticeable by naked eye. It means the stars which are brighter than 5 magnitude. So we have generally 5 small satellites. It means there was 6 of them, but 1 of them failed to communicate with ground station. So we actually are operating with 5 nanosatellites. This is the collaboration between 3 countries, Canada, Austria, and Poland. So each country has 2 satellites. Canada has BRITE Toronto and BRITE Montreal, which failed. Austria has BRITE Austria, UniBRITE, and Poland has BRITE Heveliusz and BRITE LEM. So these small letters R and B, they stand for the filter which is used for observation. So we have 2 filters, blue or red. So actually, the constellation should have 3 blue satellites and 3 satellites observing in red. Because of the failure, we have only 2 satellites observing with blue filter. So the goal is to obtain uninterrupted photometric observations of stars, so that observing the star for a very long time, it means we usually spend like 3 months observing a given field of view. So for stars, we have very long and uninterrupted light course. This allows us to reach sub-millimagnitude precision in photometry, which allows for a lot of findings, discoveries. Well, I'm not astronomer, I'm electronic engineer, so I will not talk about this, but there are already a lot of papers from BRITE data, so it's very easy to find them. Okay, so let's talk about the imaging system that we have. Our telescope, actually, it's here. This is the lens system with 3 centimeter diameter. So imagine that with such a small satellite, we were able to make a lot of discoveries. A 3 centimeter lens system, which allows for observing 24 degrees field of view. We have full-frame CCD Kodak sensor attached to the optical system. Unfortunately, it's not cooled, and we don't have any shielding. So this is the main problems which we encounter, and actually the images are noisy because of these 2 things. This is example of our field of view with Orion constellation visible. You can see the stars are marked by red little squares. So this is the field which we usually observe, because vignetting appears outside of this field. And we do not transfer the data from whole images, because it's like 20 megabytes per 1 observation, we concentrate only on stars and transfer only small rasters around stars. So these rasters can look like here. This is exactly for Orion constellation. The numbers also correspond to the, I cannot find, oh, here is one. So this is this star and so on. So what you can see here, here it's the high resolution version of our PSFs across whole field of view. So you can see the PSFs are quite complicated. I have to say, I didn't say it before, that we use defocusing. It means per one pixel is actually 20 seconds. So if you are in focus, then our star would be just 1 pixel. But the system is intentionally defocused so that the light from a star is falling off several tens of pixels. So it's like it looks. Okay, so what challenges, what problems we have? The mission started about 2013, so it's like currently we have 5 years after launch of the first satellite. Let's talk about the first thing. It should be the first one, not this one. So this is the biggest challenge in our data. Because of lack of cooling and because of lack of shielding, our CCD sensors are constantly damaged by protons. Protons are hitting CCD pixels, they introduce defects, and the defects, they generate dark current. That is the problem. And we don't have temperature stabilization. So the temperature of sensor can range from 5 Celsius to 40 Celsius. So it's more than room temperatures. So in the highest temperatures, we can see the rasters looking like that. Here, there's also a star somewhere buried in noise. So this is a great challenge, how to deal with such images and how to obtain the sub-millimagnitude precision having these problems on board. So, and this is another problem. It means the dark current, it's not stable. It means we are accustomed to just subtracting dark frames from images. That's all it works. It works on ground, but not in space. It means the problems with dark current we have here are not the same problems we have up there. So the defects are not stable. We cannot say what is the dark current generation rate in a single pixel, because it can change. It means for a few minutes, it can be higher, and then suddenly it changes to lower state, and suddenly it changes to even higher than it was before. So it's called random telegraph signals, which we can observe in the dark current. So first, temperature changes, and second, dark current also changes its characteristics. So no way you cannot subtract dark frame from this to obtain the images. And of course, the problems rise with time. So the number of defective pixels and the general amount of dark current in a sensor is growing. There's one of my papers recently published in Sensor where I show that it's a linear increase. So with time, we expect that we will have more and more problems. And one day, probably we will say, well, we cannot obtain the accuracy that was just at the beginning, the requirement for the mission. But still, we will getting data. But, well, what to do? Everything, what we can do is to try to process these images somehow to obtain reliable photometry. Another problem, of course, I forgot to tell about this, it's the problem of point spread function. It's not only that they are irregular across whole field of view, because, well, in one part, okay, here this is different than here. But this is okay, we are working with single star and the series of images in time. So we don't care about the fact that PSFs are different, but they are different from frame to frame. It is because of problems with stabilization of satellite. It's not only the CCD sensor that was damaged by the protons. It was also the star tracker. It's also affected by dark current. We don't know how the images from star tracker look like because we don't have access to this. But we can see that the PSF is slightly blurred differently from image to image. So it's not only well, it's blurring because of satellite stabilization, but this is also something a little bit different. It means it changes with temperature. So if we have 5 Celsius or if we have 40 Celsius, that PSF also grows or shrink. Yes?
But at least it will be the same for all the frames. Out of focus distortion due to misguiding will be the same for the whole CCD, presumably.
Oh yeah, of course that is true. The problem is with that this kind of defocusing or blurring. It's usually at sub-pixel scale. Oh. It means it's much harder than you have blurred through several pixels. And if you are working within a pixel size, that's much harder to estimate it. And the optical system is so well complicated. It means the defocusing is different in different parts. We didn't perform the calculations or any simulations for whole system. We are just working with a single cube of images in time for a given star. Okay, so what is the current solution for the 5 years? It is something that we've been doing for the 5 years of our mission. This is the aperture photometry applied on chopping mode. It means we quickly changed, not so quickly, but after first year of the mission, we observed the problems with dark current. And I just thought, well, okay, dark current is unstable. It means it can change, but usually for a period of time, it is stable. So we can move the telescope in between consecutive exposures, between 2 alternative positions, and instead of working on images, raw images, we subtract image from the image which was received, which was registered in a time just like 50 seconds before, because this is the difference between our exposures. So in this short period, usually dark current temperature is very similar, and also the chance that random telegraph signal can appear is also low. So here we can see the different images. There are some bright and some black pixels. There are the ones where dark current changed its state, of course, but usually most of the pixels are nearly zero. So we can see the PSFs and the stars, the intensity from stars very well. This, like, look here, you could not work with this image, but when you push the satellite in chopping mode, then from difference you have this, and you can work on such image. This is the method which we are currently using on satellites. And to obtain the photometry, we use aperture photometry, which is described on more than 20 pages in Astronomical Astrophysics. This is the article showing details of this. I will not present them. It was the topic of my last presentation 2 years ago, actually. I just only wanted to say that we don't have a circular aperture. They are customized so that they fit our PSF very nicely, and they are selected based on images. And we have several steps, which include image classification, construction of the best aperture, and also we have several steps of decorrelation. It means we have like temperature, orbital phase, the place where the satellite is currently relatively to Earth. Also, we have other things like estimation of blurring and several other parameters which are used to decorrelate photometric data. So this is how it works now. And we were considering PSF photometry at the beginning of our mission. But the general idea, well, we said it will not work. We tried some typical methods of PSF photometry that are used in for other missions or on the ground, and they could not be applied just because of this kind of instabilities of the PSF and working with sub-pixel scale. There's also a problem with this. But we expected that we should have some benefits if we found a method for PSF photometry on such images. Okay, so we know that it should work better for faint stars because the knowledge about PSF will allow us to fit better the PSF, the current PSF, and to count the intensity. And we also knew that PSF fitting might be a kind of interpolation for defective pixels. So when the number of hot pixels it was expected to rise, so we thought it might be worth to think about this, so that we can interpolate it better with fitting. And finally, this year, not this year, but a year before, I implemented the method which it works very nice for half of star. It means the fainter one, and we expect also that it will be a good solution for future as the number of defects will grow. So here are a few steps about this. Few steps of this kind of this method. So this is our difference image. Okay, we work with them. So we perform thresholding with 50 ADUs. This number taken from readout noise, and so that we are far from the readout noise in difference image. Actually doubled, because the difference image is difference between two images. So the readout noise is the variance is twice as big. So this is the value taken, and after such thresholding, we have the result like this. And we find the largest region. So this is the one. We perform dilation. It's kind of extending slightly pixels around. The same procedure is done for the negative profile. It's with this difference that we use minus 50 ADUs. So we have the mask for the negative profile also. So we have two masks. What we can do with them? We find the center of gravity in each PSF, in mask. So the image is masked with this mask, and we find the center of gravity. This is this black cross here, and the same is done for the negative profile. This procedure is very simple, as you can see. We try to find some images that we should reject. If, for example, profiles are too close, it means the centroids are less than 1/4 of the raster width. They are rejected. They are too close. If they are too far, they are also rejected because we suppose that some parts of PSF are outside of our raster. So we don't want to work with it. And sometimes when you perform dilation of this image, so you have this, and the same is done for negative, some pixels may overlap from two PSFs. So we also find such pixels, and we say, okay, the PSFs overlap, so we want to reject them. So this is just the procedure to find the images which are okay and which we can use for further analysis. Okay, so before I move to the next slide, as the output of this step, we have the images which are okay. It means some of them are rejected, and we take only positive profile. We mask this profile and we move it to the center, so that the center of gravity is center of our image. So we have a set of PSFs looking exactly like here. It means for whole set of images, we have masked and centered profiles. And this is the problem: how to fit the PSF to this kind of images, because the PSF changes with time, with temperature, and from frame to frame. So my idea was to create a kind of basis using which we can fit the PSF. So I used the PCA decomposition of PSFs. I took all these PSFs, all the images previously masked and centered, and I performed principal component analysis decomposition into so-called eigen-PSFs. This is the method. Sometimes it's used for when you want to find how PSF changes with in field of view. But here it applied slightly different. So we have a set of 40. This number was taken just because larger number of eigen-PSF didn't bring any benefits. 40 eigen-PSFs. So the first eigen-PSF is just a mean PSF. Then the second two eigen-PSFs are usually connected with the slight shifting of PSF. It's like sub-pixel shift of PSF. Then all other PSFs are responsible for various scenarios of blurring of our PSF. So with this basis of eigen-PSF, we want to fit to a given image. So general idea is to use simple linear combination of eigen-PSFs. Here are our eigen-PSFs. Here are just coefficients which we are looking for. And here is our current image, our PSF. So this is, and here is the expected noise. It's not very hard to find the expected noise in difference image because we have previous image and current image. And as we subtract one from another, it's very easy to find what is the noise. It's just the variance is summed from, it's a sum from previous image, from current image, and also the readout noise, the variance of readout noise is also doubled. So this gives us the noise estimation. So knowing the noise estimation in pixel, we can perform this fitting easily, just using least mean squares method. But still, the question is, how many eigen-PSFs we should use? We have 40 of them. But we suspected, before applying this method, that, well, for the dim stars, usually most of eigen-PSFs will be related to noise. It means they will not give us any information. While for the brighter objects, they will be better. It means the last ones, less significant, will be also connected with some kind of blurring. So our method was not very sophisticated. We just tried to perform photometry starting from 3 eigen-PSFs. It means the mean and connected with shifting, starting from 3 to 40. So a set of light curves were obtained, and we analyzed this light curves, looking which one has the lowest spread. So this is a very simple method. It doesn't take much time. So we are doing this this way. Okay. And of course, we wanted to compare the results of this method with the aperture photometry. So to compare the light curves, we used the method which was also taken and also used in our aperture photometry, in current method, which is currently employed for our data. This is connected to using some robust estimation of noise. It means our data is divided into photometric data is divided into orbits. It means when the satellites move around, there's also a period of time when we can observe. So we call this is one orbit. Then again we have another orbit. So we obtain like clouds of points for each orbit, and in each cloud we can estimate the spread. We use the median absolute deviation because we have some outliers in data, still we have them. So we use math in each orbit. Then we calculate, again, median math across all orbits. It's median because we sometimes have orbits which are more corrupted by noise. It's because, for example, we are observing, we have some stray light from moon. It happens sometimes because we are observing through 3 months. So some orbits may be corrupted, and that's why we select median over maths. for all orbits. So this gives us QM quality measure, quality metric. This was also used for the selection of best aperture in aperture photometry. Let me check the time. Okay, I can see that this will be the only presentation I will give today. Okay, what was the analyzed set of data? It was over, you see, 200 light curves. Imagine that, 2,000, sorry, that each light curve is usually 3 months long. So this is really a lot of data collected by the last 4 years. Now I would say 5 years nearly. Okay, so this is collected by all satellites, all 5 satellites in 2 filters. And we compared which quality measure is better for new photometry or for the current one. Okay, these are the results. You can see this is delta QM. This is difference between quality measure for its new minus current. So this means the points lying above the 0 means that, okay, this stars was measured better with previous photometry. But the points below, obviously, they mean that the light curve obtained with new photometry is just better. What we can see here, it's something also connected with the level of, with the degree of degradation of CCD sensors. BRITE Astra, BA, and BRITE and UniBRITE, and also BRITE LEM are the satellites which were launched as the first one. They are most degraded. There's no shielding installed in these 3 satellites. After a half year observing with these 3 satellites, we knew that something is going wrong, and we have to put some shielding, small, because we didn't have space for this. But small shielding was installed on BRITE Toronto and BRITE Hevelius. BRITE Toronto has, as far as this was aluminum shielding, just behind the CCD matrix, and BRITE Hevelius has even better solution. This is the Polish satellite. We have Borotron shielding, slightly thicker. We just found enough place. We moved different parts. So this satellite actually has quite nice shielding. And we also, in the paper that I was showing, it means the one about dark current, I am presenting results about degradation. And these results are, well, they agree very well with the level of degradation. We can see that here in these 3 satellites, we can see the fainter stars are usually better measured to using PSF photometry. This is something what we expected. And if we counted the number of stars measured better by new photometry, new photometry wins in these 3 cases. This is very similar for both pipelines. The results are very comparable in BRITE Toronto, while in BRITE Hevelius, in general, current aperture photometry wins. So, and we can see also this kind of linear relation here, that fainter stars are usually better measured by PSF photometry. This is exactly what we expected. So these 2 observations they agree very well with our expectations. What else? We also looked at the optimal number of eigens used for the fitting. And we observed also what we expected. That's very nice. It doesn't happen very frequently, but this time it happened. So we can see the stars which are faint, dim, they usually are better fitted with a lower number of eigens. It's just because the first eigens are okay. The next ones they usually are connected with some noise, so they don't mean nothing. So you should not use them. This is also visible, actually visible in all our satellites. So at the end, okay, it's like maybe too short, but I cannot start new presentation now. I hope we'll have some discussion about this. So the main conclusions from this are, of course, the PSF photometry, the one presented here. The new one is competitive. It usually is better for fainted stars. It performs better for most degraded sensor. So looking ahead for the next years of the mission, we hope that we have kind of solution for obtaining still reliable photometric data with high precision. Of course, current aperture will be applied for brighter values, which is the least degraded. I can give you the scale. It means the amount of dark current in brighter values, the amount of dark current, actually the rate, the number of the amount of dark current rising with time is like 4 times lower in brighter values than for the satellites which are not shielded. So this is something what we can observe. And of course, this kind of photometry, well, we apply this for this kind of data. Having other small satellites, observing stars, or for other purposes. And we know that on small satellites, we don't have shields, or we can install some small shields. Then defects, the problems with CCD or CMOS sensor, it doesn't matter which one is used, will slowly or fast, depends on the amount of shielding we can input there, will rise naturally. So this kind of, and also stabilization of satellite is, the precision is decreasing. So with all these problems, this is a kind of solution. This photometry you can also apply for other, maybe other photometries. I don't know, I'm not sure where you can do this. Maybe in some system which also experience shaking or so, or if the PSFs are changing with time or with temperature, with something else. We developed it for our mission, but well, it's open for everyone, of course. And well, sorry, it doesn't work. But I suppose there's nothing more. Okay, so there's nothing more from this presentation. And well, we are still, just to say the last word, we are obtaining still very good data, even with this kind of problems. We hope to work with our satellite for the next 5 years of the mission, using some maybe new methods. Of course, there is no way the precision will decrease. But still having 3 months of observations and light course, even with as a scatter and noise quite high, it's reduced just because of the period of observation. So I don't have it at this presentation, but I could see spectrum of light course with in several papers made by our researchers, and the level of noise, it's like 0.1 millimagnitude. So a lot of findings. This work for astrophysics. I'm not expert here, but they are finding some spots on stars and so on. There are I don't know, I don't remember the number of papers from BRITE mission, but if you are interested, just look inside and you will see what kind of data and what kind of discoveries they made with this data. So I think if really I have 45 minutes, I took 40, and well, I thank you very much for your attention, and I hope we'll have some discussion now.
Questions for the speaker?
Is there any reason why you chose that CCD, the Kodak?
I just have to recall if the same question was asked last time. At first, I didn't check it. It didn't select it. Sorry, I didn't select it. Probably the reason was because it's big. It's full frame sensor, so 35 millimeters diameter. So this is large. This allows you to have large field of view. But that is true. This sensor, it means Kodak sensor. Many of Kodak sensors, they have, well, it's something what I explained to BRITE team when I was invited, because actually they send satellites, then they encounter problems, and they say, well, let's look for some experts in this field. Now they asked me, and they invited me to the team. So the reason is the magnitude of dark current here and these problems is big. It's because this particular sensor has quite high voltages applied to pixels. And in this particular situation, when you have high voltage, it's very high probability that the defects will appear. It means if you took another sensor, for example, from Sony, you would probably not see this kind of problems. This is very typical for Kodak. But as far as I remember, I was talking with, I don't remember the name, Genesic. The guy, someone who is very experienced in CCDs, they sent the same sensor to Mars. And imagine what kind of problems they have. Exactly the same. So it's not only the fault of the BRITE mission. They also did it. They will not do it again, sending this sensor. And I suppose that even they didn't make any experiments with radiating CCDs. They are not very cheap. So if you irradiate the CCDs, then you would just lose the sensor. Yeah, sure. So that it was used because of size, probably because of size, and it's quite popular. Several cameras operating. I don't know if also at San Pedro Martir, if you have full frame sensor, that it's very high probability this is exactly this sensor from Kodak. And another answer for this is because this is interline sensor. It means you can observe when you read. It means you just push charge to the interline register, and in this time you can make exposure. So this was the reason. In fact, it doesn't work like this because the exposures are like 1 second. And the readout is about, I don't know, 7 or 10 seconds. So you cannot make another exposure because you don't make so long exposure, only 1 second. But in general, it can be fast. It can work like exposuring and reading out data the same time. So you don't have to wait one from another. The original idea of the mission was to make the photometry online. It means there on board. Yeah. It was the original idea. But when they encountered this kind of problem, they said, well, that's no way to do it there on the satellite, because you can see in this method, also in other methods that you used previously, you have to have whole light curve and then decide, okay, let's take this aperture, or like here, let's take this number of eigen-PSFs for fitting. So you need whole data. And to do it online, they thought that the images will be clear. So only put the aperture and take the value and send data to the ground. Only one value. Now we have to transfer these boxes, these windows, rasters, yeah, the small rasters. So this is sometimes a problem. We had some problems with radio interferences in Warsaw, and we were not able to download enough data. It means the satellites were acquiring more data that we could download to the ground. So the guys from Canada helped us, and so on. We have several. Now we have only two stations. But it's enough. They work very well. It means the transmission, the data rate, the bit rate is like above 2 megabits. So this is enough for the small rasters we are getting from satellite.
More questions?
Hello. Do you have an archive where we could see the kind of light curves, or could we have access to these light curves?
Yes, this works like this. It means there are stars that were okay. We have our PIs. They are privileged to the data. It means the field which we are currently observing. When we finish, they send data to me. I'm processing data. Then I return data, and then they give the stars only to the PIs of the stars. Sure. Okay, and then PIs, they have like 1 year or more. They can prepare article from this, or they also may say that that's data is very, very noisy. We cannot do anything. And after this data goes to archive, and there is archive for BRITE satellites. But be aware of one fact. It means the correlation, which I said that we perform a lot of the correlation with temperatures and so on. This is not included in the pipeline. This is something what you can do. It means we have a cookbook how to do it. It's a little bit of work, but we decided to just give it's your choice. You can do it your way. You can do it like it's in cookbook, but you can decorrelate it different. We cannot provide you decorrelated data because the correlated data might be unreliable. We are not sure. Only if you decorrelate and see, okay, this is physically reasonable, then you can work with this. So data still after this pipeline, this or the one which is used currently, it still has to be decorrelated because with temperature we also have some drifts. You cannot correct it in the pipeline.
But all the information to do the decorrelation is available.
Yes, there's a cookbook made by Andrzej Pigulski. This is one of our.
And if I type BRITE archive, it will come up.
It should definitely. If you can, then just write mail to me. I will find it. I don't know where it is actually. I don't care about this, but there is for sure.
Okay, more questions? If not, let's thank again to the speaker.
Thank you very much.
And we have after parties to discuss more about this.
Okay, thanks.
So we have some snacks. Yes, really? Okay. Bread.
Be nice to attend.
Yep. It's just here outside.